Thank you very much for attending this virtual presentation. I'm Christos Bergeles from the Robotics and Vision and Medicine Lab of the School of Biomedical Engineering and Imaging Sciences at King's College London. I will present to you the first robot that has been designed for optic nerve sheath fenestration. Optic nerve sheath fenestration is an invasive procedure which happens in order to reduce elevated intracranial pressure in the brain. When there is elevated intracranial pressure, this can lead both to brain damage, but also to optic nerve damage and therefore blindness. And a simple way to reduce intracranial pressure when drugs don't work is optic nerve sheath fenestration. And this involves doing a tiny incision of the optic nerve of the human eye. However, in order to do this incision, one needs to gain access to the optic nerve, and this is where things become tricky. Because what you need is you need to dissect the muscle, you need to take the eye out of the orbit essentially, you need to park it a little bit on the side, fully rotate it, remove all the fat that exists there, and expose the optic nerve in order to do a very tiny, maybe 1 millimeter by a few hundred micrometers incision on the optic nerve, and then suture everything back, put the fat back in, put the muscles back in, put the eye back in the orbit. And this tiny incision acts as a way to deflate the elevated pressure and therefore save sight. So this procedure is very, very challenging and risky and carries complications, and very, very commonly it requires reoperation, which comes with its own extra set of problems. So knowing that we can design very small flexible robots, we wanted to create a robotic system that would allow us to carry out this intervention much more carefully and with greater precision, and therefore making it accessible. The flexible robot technology that we are using is called concentric tube robots, and it comprises pre-curved super-elastic tubes that ultimately conform to a mutual shape. If I have one tube of a certain alloy, and we use night-eye, which is a super-elastic alloy, and the tube has a curvature which I can set with heat treatment or joule heating, and then the tube has also a specific length, and then I have a second tube which fits inside the first tube and has another length and another curvature, and a third tube which could be potentially longer and even more curved, and it's normally less stiff. Once I put one tube inside the other, what you have is a tube assembly where the stiffest tube always governs the shape when that tube is present. So what I can do here is I can move tube 1 in and out, and then this would affect the shape of the entire robot. But if I decide to move or rotate tube 3, then this tube would move on its own and would not affect the shape a lot because it is much less stiff. This allows me to do a coarse-to-fine manipulation where the stiffer tubes do larger alterations to the robot shape, while the less stiff tubes are essentially manipulations of the tip. This approach is better illustrated with these videos. What you see on the top row is a large-scale system, dimensions kind of like a catheter in terms of diameter, and this is at the lab of Pierre Dupont at Harvard Medical School, Boston Children's Hospital. The tubes are grasped from the back, and then they are inserted and telescopically translated and rotated with respect to one another, and this gives rise to this snake-like motion of the end effector. And we have shown that you can very, very nicely control both the shape of the robot and the tip position, and you can even adjust the stiffness of the robot to minimize or maximize the application of forces. Now, what we started investigating is how small you can make these devices, and we found that you can get these tubes very small, down 0.5 millimeter or even less, and therefore we started exploring microsurgical applications where these concentric tube robots would be used as mechanisms to augment surgical dexterity. And our primary interest is vitreoretinal surgery and in general applications in ophthalmology. So the question then is, how can we actually design our robotic system to carry out optic nerve sheath fenestration? And in order to do that, we looked into the navigation algorithms and the design algorithms that we had developed in the past. So we always split the design of our robots into two parts. First, we design a navigation section, which coarsely takes the robot to the location where surgery will be performed, and then we design a manipulation section, which optimizes the parameters of the robot, the tubes, the lengths, the curvatures, the stiffnesses, in order to carry out the surgical task. That surgical task is, in our case, the fenestration, but it could be drug delivery, it could be surgery, and you might need to optimize both for orientation or for position or for the entire pose of the robot. Now, in our specific case, what we have done is we have looked at the clinical requirements to gather the system design considerations. First of all, we must have a bimanual manipulation system because we need to have one forceps, which will hold the optic nerve in place, and a needle, which will perform the fenestration. Of course, we need to be able to visualize our workspace, and this is why we have a camera. And this camera is a 1.1 millimeter camera from Enabling with embedded illumination. The workspace that the robot needs to go and reach is indicated by this red rectangle in the figure, and the robot should cover all this workspace with a good degree of overlap between the left and right manipulators. What you can see on the bottom right of this slide is the view from the camera, and you can realize that you need to have a good orientation of the camera. Therefore, you need manipulation of a third arm that carries the camera as well. So in order for us to create the navigation section, we took patient information from MRI scans. We segmented the eye sclera, which is the white part of the eye, and created a patient-specific collimator, which comprises two cannulas and an open channel from where the camera is passing. Now, this collimator, this cannula, can be sutured on the eye sclera, and suturing stuff on the sclera is something that clinicians do routinely, for example, in cases like scleral buckling. So we now have this construct, which is our navigation section, and through that we have the tubes of the concentric tube robots that would pass in order to reach the workspace indicated in red. And now the next challenge was to identify the curvatures and the lengths of the robot tubes. And in order to do that, we went to our computational robot design toolbox, and we iterated over different robot curvatures and different tube lengths in order to figure out how the two arms can maximally reach the workspace in red while also being able to perform the bimanual tasks. Now, on one hand, you want increased reachability, which is a 3D requirement, and you can voxelize the workspace, and then you can make sure that the robot can reach all these voxels. But on the other hand, you also need increased dexterity. And in order to evaluate increased dexterity, we developed a new process, which we are about to publish, how we voxelize SO3, so the orientation space. So by voxelizing 3D space with classical discretization of the volume, but also SO3, now you have a way to discretize the entire set of poses of the robot and place this into computational design frameworks that maximize both reachability and dexterity. But that said, we had the parameters that we wanted in order to be able to reach the workspace dexterously and, of course, follow the curvature of the eye and avoid the muscles and so on and so forth. Now, the next task was to see, well, what platform would we evaluate our robot on, because there are no phantoms that exist. So from these MRI scans of the patients, we segmented all the anatomical landmarks, and we collaborated with the Royal College of Art in order to create a very realistic eye phantom and a phantom of the orbit. So we created the muscles and with different types of silicone, and then proceeded in painting everything, adding the vessels, the optic nerve, the suturing approaches. And now this gave us a very, very realistic and good-looking phantom on which we could evaluate our robot. Now, of course, looks is one thing, but a conformance and agreement with the normal biometric characteristics of the eye, like stiffness in particular of the optic nerve, is very important. So the next step was to characterize the properties of the phantom that we created in comparison with ex vivo tissue. So we took porcine eyes from abattoirs, and we started measuring the stiffness of the optic nerve through a blunt needle. We measured the forces exercised and the displacement, and this gave us a stiffness of along the optic nerve. And then we evaluated the stiffness of the phantom that we have, and we saw that they are more or less in agreement. In other words, if we are able to manipulate and do an incision and generally work with the phantom eye that we have with regards to its optic nerve, we are at least as good as if we were working with a porcine eye. And now the porcine eye is also a good model of the human eye and actually a little bit stiffer. So if we are able to do manipulations on the phantom eye and on porcine eyes, then we are good to go in the sense that our robot is able to meet the requirements for force delivery and navigation that you would have in the clinical application involving human tissue as well. And so now we know that the phantom that we have in stiffness with regards to the optic nerve is similar to the porcine eye. And then we created our robotic system based on the designs that we have. This is a simple device where translation and rotation of the tubes is controlled through these knobs that you see. And then we were able to deploy it within the phantom eye and visualize whether we can reach the location of interest, whether we can grasp the optic nerve, whether the camera has the appropriate parameters, and so on and so forth. And what you see here is one hand will in a while be controlled in order to reach the optic nerve. The optic nerve is this white transparentish construct, and then you are able to poke it, and in general you get a sense of how you would navigate in this small cavity. So all looks good. We know that the stiffnesses are more or less appropriate, but what we didn't know is whether we can actually do the cannulations and the fenestrations that we had. So this brings us to the next experiment. There are no data in the literature about the forces that are required in order to perform the fenestration of the sheath, and so we created, we gathered this experiment by penetrating porcine eyes. So we mounted electromagnetic sensors on a tip of a needle that will do the penetration, and then we measured the forces on the porcine eyes, the various porcine eyes, and identified the margins of the forces that are required in order to pierce the sheath and finally the optic nerve. And you can see these illustrated marks on the figure, where at first you have a small jump in the force, and then this is the penetration of the sheath, and then afterwards you penetrate the optic nerve. And of course, this gives us a sense of the forces that our robot should apply. And then we went on to evaluate the forces that the concentric tube robot can apply, and we found that indeed they are of the same magnitude, and therefore we can now navigate within the eye cavity. We have a good concordance between the stiffness that the phantom has, and we also know that we can apply the forces required in order to cannulate the optic nerve. And so then we took our robot, again similar setup. We mounted the robot on an ATI force, the porcine on an ATI force sensor, and we started doing penetration experiments for various size to understand the forces that must be applied, whether the robot can apply them, and so on. Now you can see the robot is approaching here from the other dimension, other direction rather than the sclera. It was very hard to decouple the forces that the collimator was applying on the eye, so we thought we should suspend the collimator rigidly and then just have the puncturing effect from the needle held by the flexible robot. So, in other words, to conclude what we have done, we created the first robotic prototype for optic nerve sheath fenestration. The robotic prototype will be able to access the optic nerve with a bimanual manipulation system and then perform fenestration, which is a small cannulation of the optic nerve. This system was designed based on a computational algorithm and ultimately was evaluated with regards to ex vivo experiments involving porcine eyes and a bespoke phantom that was created based on MRI scans of patients. Thank you very much for your attention, and I'm happy to take any questions in the Q&A session that will follow. Thank you. And you can follow us on Twitter and also on our GitHub channel, where we routinely post software as open source should you want to use it in your experiments.